Hi everybody. We are going to go through the concept of quantum numbers. So this is in the field of quantum mechanics and the electron cloud model of the atom. So let's get started with this. We'll get right to it. The precursor to this will be if you were watching the lesson or reviewing it about the history of the atom through all the discoveries of the different scientists. So we quickly went through that, and the summary of that was with the Bohr-Rutherford diagram, it was oversimplified and only applied to the hydrogen atom, and it had to do with the fact that electrons can't move in circles or else they're accelerating and require a constant source of energy. That's the basics of it. In theory, these quantum numbers instead, or the quantum mechanical model, describes an electron as having wave properties, and those wave properties can be described with a wave equation made up of 4 different variables. Those variables in turn describe 4 properties of an electron, an individual electron of an atom. So that's what we're looking at here today. So the images you see on the title slide here are all different movement patterns of electrons, with the nucleus being 0, 0, 0. We're working with an X, Y, Z coordinate system. Okay, so that's in 3D. And again, 0, 0, and 0, which is in the middle, would be the nucleus. So an electron can only move so many different directions away from that. So the quantum mechanical model of the atom, it has to do with the idea of electron clouds. So things do not move in circles, but they move in patterns instead. So from the previous topics, the uncertainty principle, if we know the path of the electron, so which way it's traveling or kind of the line it's taking, we don't know how fast it's moving because we would have had to stop it. If we know how fast it's moving, we can't know where it is because it's moving too fast for us to figure that out. You can see why this is called the uncertainty principle, because we can only know one or the other, not both at the same time. So the problem with this Bohr model that we have is that there were fixed paths, meaning that electrons just moved in circles around the nucleus. Okay, so with a better understanding of forces in physics, circular motion requires acceleration, and any kind of acceleration requires a force, which requires energy. So because that does not happen, all right, through the modeling using waves, what we come to understand is that electrons have random motion, and they can behave like a wave or a particle. So that's called duality. The idea is that when they act as waves, right, they exist in certain energy levels, they can interfere with each other, and when they act as particles, they have properties that allow them to interact with matter. So the quantum model describes probability, where the electron can be. All right, so electron probability graphs are called orbitals, and they show us the probable location of an atom. In a Bohr diagram, if we drew an electron on the orbit, we'd say the electron's there. It's in the first energy level. But now what we're saying is, you'll see on the next slide, is that electrons actually move in 3 dimensions, right? And they move in random patterns. They don't follow a circle. Again, this is not what they do. All right. Instead, imagine a 3-dimensional sphere, an electron in there, kind of bouncing off the walls in all directions, and that's its path. It's a random path. Okay. As we talk throughout this lesson, notice the difference: orbit and orbital. The orbit refers to the Bohr diagram, which is the question here. The orbital describes the path or area of the electron for the quantum model. So here's what it looks like. This is the first energy level, right? So what we know as a circle, you can kind of see it superimposed here for the Bohr diagram, is actually a 3-dimensional sphere. So this positive charge in the middle represents the nucleus, and all these little dots do not represent individual electrons. It represents where the electron can go. So it's the electron path. And it's basically made up of photographing the electron infinite amount of times and superimposing all those images. So if I take one picture and I see the electron there, I see another picture and I see the electron there, Do that an infinite number of times, superimpose them all, and you get this graph. What this tells us is that in the first energy level, the electron really only moves in this circular path, right? And it can only get so far from the nucleus. So it's got a set distance before the attractive force breaks free. So if it tries to get too far, the nucleus pulls it back in. The darker areas, you can see that there's dark versus light, represent where the electrons are found more often than not. So they're usually in that darker area, but they can go into the lighter area as well. And then image C just tells us that that is in 3 dimensions. Okay, so the shading is how many more times it was found there than on the outside. Okay. So again, the keyword here is probability. You are likely to find an electron within this area. It does not mean you will be able to pinpoint exactly where it is every single time. So to describe where the electron is, we use 4 quantum numbers. All right, and for an electron, it's usually described 1, 2, 3, and 4, side by side. And what it's going to tell us is where do you think the electron is relative to the nucleus of the atom. So an analogy for this, I'll just jot that down here. Right? It's like where you live. You live in a country or province, a city, you can be very specific. In a neighborhood, you have a house in the neighborhood and you sleep in one of the rooms in the house, wherever that might be. So you can describe your location pretty well. Electrons are the same. We can describe what energy level it's in, what direction it's moving, what the shape of the path it's moving in is, right? And that's everything that these numbers will describe. So that's our goal here. Describe an electron's location and motion using these 4 numbers. So we'll get right into it. The first number is called the principal quantum number. Right, so this is represented by the variable n. So if we line these 4 numbers up, the first one has a variable n. This is the energy level, or the size of the energy level. All right. Another way of describing this is its distance from the nucleus. As this value goes up, the size of that shell or energy level gets bigger. Right? It gets farther from the nucleus. So this number can exist as n can equal 1, 2, 3, any whole number integer above 1 or including 1. So if we look at the chart here, the primary quantum number, if the quantum number is 1, okay, that means it's the first, you can think of it like shell. If I draw a Bohr diagram here, 1, 2, 3, 4. As the number goes up, the shell gets further from the nucleus. Right? Now, each shell, you learn this pretty early on in your scientific career, can hold a different number of electrons. That's determined by this formula. So the number of electrons is determined by 2n squared, where n is the energy level that it's in. So an electron in the first energy level has a value of 1. So we would say 2 times n squared, so 1 in this case. The first energy level holds 2 electrons. The second energy level, 2 times 2 squared is equal to 8. Third, 2 times 3 squared. Energy level is equal to 18, and then so on. Right, up to the 7th level as is. This pattern should go past infinity though. Right, so the next element's going to be very important. At the time of recording this, there are only 118 elements on the periodic table, filling the 7th energy level. So if we do that, when we look at the 7th, if we say n equals 7, we ask ourselves, how many electrons can the 7th energy level hold? Pause and try this for yourself and then resume. Okay, so hopefully you try that. So to determine the number of electrons, we just do this equation here, 2n squared. So that means 2 times 7 squared. So the 7th energy level can hold 98 electrons, plus all of the other energy levels below it. Now the 8th, if we do 8 squared is 64 times 2, the 8th energy level should be able to hold up to 128 electrons. So that's why the next discovery is going to be important. So first off, n basically describes the size of the energy level. How far can the electron move from the nucleus? The second number in our series, 1, 2, 3, 4, we've got n, which represents size, is the azimuthal quantum number. We're going to just call it L. All right. So this describes what's called the angular momentum. All right. Another word for that is just the shape of its path or shape. Okay. So think of it as being in a room. If you enter a room and the room is square shaped, okay, you can only travel, no matter how many random directions you run in, you can only travel in a square confine. If you enter a star-shaped room, you're going to move randomly in star-shaped patterns, and you'll cover all the area in that shape. Electrons are the same. They can only move in the path that their shell or their energy level has a shape of. So, what does this mean? Well, there are lots of different shapes and patterns, but there are four main ones. Well, there's many more, but there's four we're going to look at. So, the first shape is a sphere. It's a 3D sphere. So we call that the spherical shape. Pretty straightforward. So that has a quantum name. It's subshell. So its shell would be the energy level. Its subshell would be called sharp, or the s orbital. And that's another word for this. Okay, it's a sublevel of the energy level. So these numbers can exist, all right, within a set range, and it depends on the first number. So if the first number, actually, let's scratch that. For the numbering, n can be 1, 2, 3, 4, 5, 6, 7, all the way up depending on the number of electrons we have. The second number depends on the first number, and remember that this depends on a specific electron. So one set of four numbers only applies to one electron. All right. So for the second number, it has this value here. It can be from 0 all the way up to n minus 1. So for the first energy level, if n is equal 1, that means the second number can be 0, and because n minus 1 is 0, that's the only option here. So what does that mean? The first energy level has what's called an s orbital, all right, which is a spherical shape. So any electron in the first energy level can only move in a spherical pattern. An electron in the second energy level, okay, so let's look at this here. We're going to have options. L can be 0, okay, and it continues all the way up to n minus 1. So if n is 2, 2 minus 1 is 1. Right? And they're only whole number integers. So an electron in the second energy level can travel with an s orbital, or now what's called a p orbital. So if we go to our chart over here, when the second number is 1, that's a p orbital, and that's a dumbbell shape, or like a three-dimensional figure 8, if we draw that. So that electron can be in one of those two shapes, okay, but not both at the same time. Remember, we're describing one single electron with this. Now, depending on the energy level, it's going to affect the different shapes, so you can get a bunch of different unique ones here. We're just going to focus on these shapes here, okay? The names of the orbitals are S, P, D, and F, and then after F, it just goes G, H, I, J, K. It follows the rest of the alphabet. Okay, that's the naming convention for it. So first number is size of the orbital. The second one is the specific shape of it. So if I have a sphere in the first energy level, it's going to be smaller than a sphere in the second energy level. Right? That's what the first number describes, and the second one describes what the shape actually is. Right? We'll leave it at that. So now if you're wondering from here, well, how do I know if it's 0 or 1? You'll have information to tell you that. Okay, we don't just pick numbers or pick random electrons. We're usually applying this to some kind of data that's been observed. So if you're told, okay, the electron is in the p orbital, well, then you know the second number describing it in the set has to be 1. Right? We say it's in the third energy level, okay, then it has to have a value of 3 first. Okay, so there will be data to support this. The third number, called that magnetic quantum number. So let's jot these out again. We've got N, we've got L, and now we have ML. So first we have the size, then we have the shape, and now we have the direction of the shape. Okay. So because we're working in a 3D world, what we've got off to the side here is a 3D grid. So we've got X, Y, and Z coordinates. Just put that there. So the shapes, depending on what the shape is, can be pointing in certain directions. So a sphere covers all three directions at once. So an electron can move in all three dimensions in a sphere. It just moves in the sphere. A dumbbell, you can imagine a figure 8, is a little more linear. So for example, this dumbbell here, if I color it in, it's lying on the x-axis. So even though the electron's moving in that kind of dumbbell shape p orbital, it's doing that in the x dimension. So it can only move kind of this way. That electron's not going to move up and down or side to side in space. It can do that within the orbital, but the orbital is lying on the x-axis. So the electron has to stay in that pattern. And that's what the third number tells us, what direction that orbital is pointing in. So in terms of values, okay, you can see it here. It's negative L up to positive L and every integer in between. So if we're told that an electron is in the p orbital, that means its L value is 1. And again, it changes for every electron. So that means the third number can be any value from negative 1 up to positive 1, and we only have 0 in between there. So those are the possible numbers. It's not going to be all three. It'll just have one of those. And we'll see what number corresponds to what in a second. All right. So each one of these shapes is called a lobe, and each lobe can hold 2 electrons. So for example, this is a lobe. 1 electron can exist on one side, and the other electron can exist on the other. If the p orbital is made up of 3 of these lobes, each of 2 electrons, and we'll kind of just draw them on their axes like that, right? The p orbital can hold 6 electrons. So we're starting to put some things together. So that's the direction and the shape of these. Now, why is this important? Well, think back to the Bohr diagram. What did the third energy level in a Bohr diagram look like? Just a bigger circle than the second. So again, it's not accurate because the electrons don't move in circular paths. We're starting to observe them now. So we describe the size of the orbital, the shape of the orbital, and the direction that it's pointing. Okay, the orbital. So here's a summary of the first 3 numbers put together. The first set of numbers, again, will tell you what energy level the electron is in. Okay, and again, you'll have data for this. The second set of numbers will tell you the orbital, which is its shape. Okay, so you have S, P, D, and F here. The third set of numbers will describe to you, I'll just write orientation here. Okay, what direction it's pointing in. And again, what direction the orbital is pointing in, so you know what plane it's lying on. So now we're describing how far from the nucleus the electron is, what the shape of its path is, and the general direction in space that it's traveling in. Kind of like bouncing, right? If you bounce a bouncy ball straight up and down, it's bouncing in the Z plane. All right, so here are all the individual shapes of the different sublevels. Okay, so the S orbital is a sphere. Okay, the p orbital is made up of 3 dumbbells, so they're separated, but in reality, they're actually superimposed on each other. So to put those together would look like this. Right, you get this flower shape. So this is why we separate them to see it. And remember, each lobe that you see here can hold 2 electrons. So the p orbital is made up of 3 lobes. P orbital has 3 lobes. If each lobe can hold 2 electrons, right, we'll put that here. The p orbital can hold 6 electrons. The d orbital has 5 lobes, so it can hold 10 electrons, and the f orbital has 7, so it can hold 14 electrons, right? And these are what get added up to determine how much, or how many, electrons an energy level can hold altogether. So if you look at this, what does the numbering represent? So you can see -1, 0, and +1. So for the p orbital, if the lobe is lying on the x plane, okay, we don't write x for the number. Remember, these are 4 numbers that describe the electron. If that third number is -1, that means, and so let's say it's just 2, 1, and -1. So this number tells us it's in the p orbital, and the third number tells us it's along the x plane, so we say it's in the px lobe. So this is called px. Z, where the orbital is pointing up and down, okay, the line connecting the two nodes of it is the pz lobe, okay, and that has a value of 0, and then py has a value of +1. So px negative, 0, and +1. So that's what you'll be responsible for, understanding the s and p orbital. The d orbital is not too much more complex. The only difference is that if you look at the shapes connecting them, they're pointing in the x and y axis, right? So if I draw it there, a line, right, connecting the purple lobes, it's between x and y. Same thing with the light blue ones. So d with a value of 2, that would be called the dxy lobe. Okay, and that has a value of +2. So we're not going to represent that, but that's what the third number represents, what direction it's moving in, okay, or what plane that shape is lying on. So the last number in this set, and again, every single electron has its own set of numbers. I'm going to recap this one last time. You have N, L, ML, and they have their own formula, and finally MS. You have size, shape. The last one, simply enough, is the spin number. So this is related to its magnetic field on a more complex level. But in general, we just say there's 2 possible values. The electron can have either a +½ value, which is a clockwise spin, or a -½ value, which is counterclockwise. And you can see terms up and down. We'll refer to those after as well. And that's it. That's just describing what the electron is turning. So those are the 4 quantum numbers that describe an electron. You'll have data that either gives you the numbers and asks you to interpret what they are, or they'll be interpreted and you'll be asked, what are these actual values representing? So as a summary, okay, what you're looking at here is the p orbital. Okay, you can see that they're all together. The red one represents the y, blue x, and black z. So there are 3 independent lobes, right? And they each hold 2 electrons, okay? So the size of the orbital would be the first number. The second number tells us it's the p orbital, its overall shape, so this flowery looking shape. The third number tells us which direction it's in, so which dumbbell we're looking at, red, blue, or black. And the fourth one just tells us which electron we're looking at. So are we looking at the half electron or the -½ electron? And they each occupy a different side of the lobe, which is called a node. So, lobe and node. Lobes hold 2 electrons, nodes hold 1. 2 electrons, 1 electron. Hopefully that helps. Here's a 3D representation of it. You can see the 1s orbital. There's the nucleus right down there in the middle. The 1s orbital is a sphere overlapping that. The 2s orbital is a bigger sphere. Okay, so it's still a sphere because it's s, but it's bigger because it has a 2 in front of it. The 3s orbital is an even bigger sphere. The 4s orbital is going to be an even bigger sphere. All right? And then you have the different shapes in between that. So the 2p orbital here, all right, those are dumbbell shapes overlapped with each other. 3p orbitals would be even bigger than those ones. There are no 1p orbitals. Why? A p orbital is a value of 1, an L value. L can be any value from 0 up to -1. If n equals 1, L can only equal 0, which means the first energy level only has an s orbital. If I go back to this chart here, here's a description of that. I'll just shorten this. Level 1, s orbital. Level 2, s and p orbital. Level 3, s, p, and d orbitals. Okay, so every level gets an extra orbital for it to use. And that's why they can hold more electrons as we go. So, for some examples, here are a set of quantum numbers. Let's describe the electron. So size, shape, orientation, and spin. So n equals 1. The first thing that tells us is that this electron is in the first energy level. L equals 0. Well, when L equals 0, that means it's in the s orbital, which is a sphere-shaped shape. The third number describes the XYZ orientation. So if that's our XYZ plane, and we have a sphere overlapping all of those planes, we just say the electron is anywhere in the sphere or XYZ direction. Really, they represent the same thing. The last one, because it's a positive value, it means the electron is spinning clockwise. Now, it doesn't literally mean spin, we just simplify it, but it has to do with the relation to its magnetic field. So, using that, let's look at this one here. And I'd like you to pause as you're watching this to try these yourself based on that first example. Not just copying down, but they're here if you need some guidance. So n equals 3 represents, and I'll pause, which means you can pause and think, and then come back when you're ready. The third energy level. So this would be like the third circle in a Bohr diagram. L equals 1 means a p orbital, which is that dumbbell shape. ML equals -1. So don't forget, this is representing your XYZ planes. Okay, if you go back to this diagram here, -1 represents the px lobe. So we would say here the electron is in the px lobe. And then it has a -½ value, which means it's spinning counterclockwise. And that's important on a side note. That's important for constructive and destructive interference. Okay, so let's look at the last one. You can have a pause and try this yourself if you'd like. The first value tells us the third energy level. The second value being 2 tells us that is in the d orbital. Okay, again, though, that tells you the shape. And that was on one of our earlier slides. The third one, +2 value, if you go back to that other image, tells us it's on the dxy lobe. Okay, so that lobe is a little bit bigger than the px orbital. And then because it's negative, you should be able to recognize that it has a counterclockwise spin. So that's the kind of information you can expect from these energy levels. You can pause, rewind that, and rewatch it if you need to. So here's some practice filling in all possible quantum numbers, right? Each set is capable of describing one electron. Okay, and there's an answer key to go with that if you'd like. Just showing that if an electron is in the third energy level, for example, it can have a first number of 0, 1, or 2. If its first number is 0, it can only have a third number of 0. Okay, and then it can have a positive or a negative half spin from there. So these are all our possibilities. Okay. So as a review, we talked about energy levels, orbitals, and subshells, understanding what those terms are, what the quantum numbers represent, allowed numbers, and knowing the different lobes of the p orbital, which were px, py, and pz. So in terms of numbering, we had -1, +1, and 0. And that's labeled on our diagram from before. So in terms of homework, we've done that together, labeling the orbitals. You can focus on these here. And to read differences between the Bohr and quantum models, you might want to try creating a Venn diagram as a study technique. or you can read the summary that I've got here on the last slide. Thanks for watching. I hope that helped, and good luck with the practice questions.